Hey physics students, welcome back to another edition of Rapid Review for Honors Physics. Today we continue our discussion of waves. Our focus today is standing waves. There is no better way to understand standing waves than to see a simulation. And I have to say, I have to repeat my disclaimer from earlier. A lot of what you will learn in this segment of the class when you study waves is from playing around. There are several good simulators out there. I will not run the simulators in my videos here for rapid review, partly to encourage you to go play around with them, and partly because I'm referencing work that other people have done, and I would rather link to them, which I will certainly do, and have you go to their websites to use their simulators rather than run them on my video. Okay, so we're back now. Here's a simulator, one of several you might find online. I will link to it again. It's a simulator that shows you how a standing wave will form. And it uses, as we explain what happens in the simulator, I'm going to use a lot of vocabulary. I'm going to use those words one at a time and build up a story about how standing waves form. Okay, so go with me on this. This is a step-by-step story. The story starts here. We have a wave. It's represented by the, let me call that the red wave. It's moving to the right, as I show here, and it's just moving right along at some velocity v. Okay? When it gets to the end, it's going to bounce off the wall, and it's going to reverse its direction. When that happens, it's going to turn blue so we can keep track of it. Okay? So if you're with me so far, there's a red wave going left to right, and soon there will be a blue wave reflecting off. Let's look at what happens with them. The first thing that happens is there will be some interference. Let's review, right, what we mean by interference. If two waves meet, they will interfere either constructively or destructively. Remember, constructive, the two waves add because they're on the same orientation, or destructive because they're opposite orientation, okay? And you also know that reflections can happen. We just discussed that, right? In certain situations, the reflection will come back in the opposite orientation. I would use the word polarity if I was talking about an electronic circuit. Let's see. Then they will interfere, as we just discussed. And here is the big deal. And here's, I'm saying a lot. For a given velocity, and given, you have to know v and you have to know the length of the medium, if you choose just the right frequency, and we'll discuss what that means, which frequency that is, then the interference is going to be timed. So there are locations where you'll get constructive and destructive interference. Boy, did I just say a lot there. Let's take a look, break it down a little bit more, right? What is happening there is really interesting because it creates situations where in space you have no motion of the wave medium, and in space you have locations in the wave medium that are moving a lot. It's important to remember what coordinates you're looking at. I'm going to try to emphasize, if I'm drawing a picture of time, a graph of amplitude versus time, that's one graph. If I'm looking at amplitude versus position, or position of a wave medium versus position, that's a different graph. So be careful with your axes. Right now I'm showing really position versus position. There's y displacement shown by the up and down, and there's position along the wave medium shown left to right. Okay? So if you take a snapshot in time, reminder, there's no time in this graph here. If you take a snapshot in time, you'll notice that the waves are constructively interfering. And when they add together, the blue wave, which you can hardly see there behind the red one, adds to the red wave, and you get what's shown in black. You get a big amplitude. But if I choose a different moment in time, here on the right side of the picture, you can see by now the blue wave has moved to the left, as it likes to do, and the red wave is moving to the right, as it likes to do. You can see at this moment in time, the waves are destructively interfering, and their sum is what's shown again in the black. It looks almost flat the way I captured it. There is a point where it's precisely flat. Okay? So what's interesting, though, is that all times there are locations that are not moving. These are the nodes, right, of the standing wave, and I did that wrong. Let's see, let's fix that. This is a node, this is a node, and this is a node. Those nodes never move at any time. So you can identify a location on the medium, and you can say, that's a node. And you could watch that forever. It's not moving up and down. Even though the wave is traveling, there's a wave going one way, there's a wave going the other way, there's nothing happening at the node. That's pretty cool, actually, I think, to observe. Okay? So that's called a standing wave. And we've claimed that if you add energy at just the right frequency, you're going to get a standing wave. Here I show a schematic picture of, let's say this is a spring lying on the floor, a big long spring of length L, and somebody's shaking it. You could shake it from one side and watch the reflection, or you could shake it from both sides if you do it the right way, and you'll get various standing waves. I'm showing two possible standing waves here in the picture. The key is that you have to find just the right frequency, and just the right frequency means V over lambda, okay? So in a lab, you might have tried this, or if you have access to a spring, check it out. If you have access to a rope, you can actually do it with a rope on the floor, and you can check it out, and if you can kind of discover the correct frequencies to get these different shapes, these different patterns of the spring. For example, here I show 3 different patterns you might make, and they are just different kinds of things you can create. So I encourage you to try it. If you absolutely cannot, I will include this link in the notes for the YouTube video, so you can go to that YouTube video and check it out and see people doing that. But always better to do it on your own. So in the lab or in your experiments, you'll discover that V equals F lambda. The F that you require is the F that solves that problem. We're going to say more about that in our next video. We're going to quantify that, and we're going to talk about what kinds of patterns are possible. We'll save that for our next video. I hope you'll join us for that.